Welcome everybody to geometric processing session of the SPM 2020. My name is S Sajavičius and I will chair this session. So we are going to have 3 presentations here, but before we start, let me remind some in-house rules. So we have 25 minutes for each presentation, and this includes also questions and answer session. During the presentation, the microphones of all attendants should be switched off. However, everyone is very welcome to ask the questions after the presentations. So to ask the questions, please just press raise hand button and wait until your microphone will be muted. In addition, the authors also will be very happy to discuss in Discord platform, where you can also find uploaded papers as well as presentations. So the first presenter today is Mr. Fang. He's a PhD student at the University of Science and Technology of China, and his major is in computer graphics, including geometric processing and modeling. And the title of his talk is Metric First Reconstruction for Interactive Curvature-Aware Modeling. So, please.
Can you hear me? Yeah.
Yes.
Thanks for your introduction. Hello, everyone. This is Qin Fang. I'm glad to be here to present our work, Metric First Reconstruction for Interactive Curvature-Aware Modeling. Curvature is a geometric attribute which describes how bent a curve or surface is. Here we show some common surface curvatures, such as principal curvature, Gaussian curvature, and mean curvature. Curvature is widely used in geometric processing. In mesh editing, fairing and simplified operations perform mesh surgery based on curvature values. In shape analysis, the curvature distribution can be used as geometric features for mesh segmentation, sampling, and shape recognition. Another application is to model shapes by manipulating curvatures. Our work falls into this category. The goal of this paper is to interactively model shapes by controlling curvatures. Given a source mesh, we calculate the curvature and modify its distribution. Through the reconstruction algorithm, the target shape can be generated. There are 4 requirements in this process. First, the connectivity should keep unchanged. Second, the curvature of the output model is consistent with the target curvature. Third, the mapping distortion from the source to the target should be small. Finally, the algorithm should be interactive. Interactive shape reconstruction remains challenging. The objective function is the sum of 2 energies between the source and the target mesh. Here, E curve measures curvature difference. EDIS measures mapping distortion. The 2 energies are highly nonlinear and non-convex. It's hard to optimize them efficiently. Curvature flow evolves the shape over time to meet the target curvature. According to the type of curvature, these methods can be divided into intrinsic flow and extrinsic flow. However, they usually focus on one curvature, which is not enough to determine a general shape. Now, we list some related work. Again studies allow reconstructed shapes by manipulating two principal curvatures. The energy is highly nonlinear and the optimization is time-consuming. There are some Gaussian curvature flows to generate conformal maps. Gaussian curvature is an intrinsic curvature, so it can determine a surface in 3D space. The mean curvature is an extrinsic variable of the surface. Optimizations of mean curvature only focus on generating a constant mean curvature surface. The main contribution of this paper is an interactive reconstruction algorithm to model shapes from curvatures. It contains a progressive strategy to accelerate the intrinsic metric recovery and a local global solver for extrinsic shape optimization. Based on this tool, we propose 3 modeling operations: curvature preserving deformation, curvature-based feature editing, and spherical and cylindrical parameterizations. Now I will introduce our algorithm. Our key observation is that in discrete conformal mapping, the target Gaussian curvatures can induce a target discrete metric through an intrinsic flow. This discrete metric satisfies both Gaussian curvature and conformal mapping constraints. Based on this, we divide the curvature difference energy into mean curvature term and Gaussian curvature term. Then minimizing Gaussian curvature difference and conformal mapping distortion can be converted to minimizing the distance between the current metric and the new metric. Now I will illustrate the pipeline. Given the source model and the target Gaussian curvatures, through intrinsic metric recovery, we can get target length of each edge. The edge length energy and the mean curvatures energy are minimized in extrinsic shape optimization to get the new position of a vertex. In intrinsic metric recovery phase, we choose Calabi flow, which exponentially converges the current curvature to the target curvature. As shown in the blue rectangle, the convergence rate will slow down when K approaches KT. Su et al. Proposed an approximate Newton's method. This method can be used when curvature is close to the target. So a hybrid optimization was used. However, the convergence rate before changing to approximate Newton's method is also slow. We propose a progressive strategy instead. Given the initial curvature and the target curvature, if they are not close to each other, approximate Newton's method is inaccurate. To avoid this, we approach the target curvature step by step. In each step, The curvature difference are kept in delta, so that approximate Newtons can be used. To obtain curvature value for next step, we interpolate current curvature and target curvature, and choose to make the step length small enough. As indicated by the blue polyline, our strategy converges efficiently. In extrinsic shape optimization, we use a local global solver to solve edge length error and mean curvature difference. Auxiliary variables are used. For edge length, we introduced Li to divide it into two square forms. For mean curvature difference, a similar HI can be introduced. Then a local global solver can be used for this new energy. First, we fix the vertex position and minimize the L and H energy through local step to get new Li and Hi. Next, we fix Li and Hi. The global energy is only related to vertex position. By a global solver, we obtain new position Vi. We repeat the local global step until convergence. Based on the algorithm, we introduce 3 modeling operations. In curvature preserving deformation, we move the red vertices and fix the blue vertices. The Gaussian curvature and the mean curvature remain unchanged. After reconstruction, we can get the deformed shape. In curvature editing operations, we can fix the mean curvature and modify the Gaussian curvature by increasing or decreasing its variance. The output models are shown. For different lambdas, different parts of armadillo are exaggerated. We can also fix the Gaussian curvature and modify the mean curvature. By controlling lambda, the detailed features are smoothed or enhanced. In conformal parameterizations, we map a part of the total model to a spherical shape. For interior vertices, the target curvature value can be given directly. For boundaries, we assume there are circles to determine the target curvature value. Also, we can map it to a cylindrical shape. The target curvature can be set similarly. If we map a part to a sphere or a cylinder, we need to process other parts to assemble them together. First, we scale the other submeshes to make their boundaries in same length. Then iterative closest point algorithm is used to align them. Finally, a Laplacian smoothing is used to merge them. Here we compare our reconstruction algorithm. In metric recovery phase, as shown in the table, we can see the energy of our progressive strategy is about 1% of the energy of approximate Newton's method. And the running timings are almost the same. We compare our shape reconstruction results with Su et al. In spherical parameterization. They reconstructed the shape by assembling triangles one by one. This strategy will accumulate numerical errors, causing flipped and degenerate triangles. Our global optimization can distribute numerical errors evenly. Now I will briefly show the design phase. Given the input models, we partition them into different parts. Then we select one part and edit it by 3 modeling operations. We can get an intermediate model. Next, we can choose other parts for editing. This phase is repeated until generating satisfactory models. We show the interactivity of our curvature modeling tool. We record the average time cost of each operation on different scale meshes. Meshes within 10,000 vertices can be modeled in 1 second. In conclusion, we introduce a metric-first reconstruction algorithm to interactively model shapes by manipulating curvatures. It contains intrinsic metric recovery and extrinsic shape optimization. And we provide 3 operations to generate creative shapes. Our method has some limitations and future work can be developed. For example, poor triangulation will severely slow the convergence of the discrete Calabi flow. Another point to be improved is that our algorithm takes about 10 seconds when the mesh vertices scale is 100,000. Thank you.
Okay, thank you very much. Are there any questions from the audience? Please raise your hands or just ask in chat. Okay, maybe then I have one question. So question is regarding your user study, which you mentioned in paper, but not mentioned here. So can you tell us more about that user study? And my question is, what was actually the goal of that user study? What exactly participants of that user study were asked to do?
Okay, the user study we perform is to want to prove the reconstruction tool's ability. We want to prove it's easy to use them. And usually there needs 10 to 20 operations to create a desired model. Yeah, and
Okay, but then you gave the model, like, as you said, like the users were dealing with this system until they get satisfactory results. So what actually you mean by satisfactory result? It's some target model or the result they wanted to model?
Our reconstruction tools many design the cartoonized models. It's not a realistic model.
Okay.
It converts the part of model to a sphere or a cylinder.
Okay.
So the desired model is what the users want to design by our reconstruction tools. So it's low, there is a low criterion to design, to judge it.
Okay, Thanks. And we have one question in chat. So question is, how did you choose the target mesh? Is it defined by curvature or some input mesh?
Sorry, can you pattern your question?
So can you see the question in chat?
Yeah. What this page?
Okay, so there should be some slide at the beginning of your presentation where you introduced target mesh.
What slide? Sorry.
Sure. I have a question about how did you choose a target mesh? So maybe at the first or the second page, I can't remember it. So you have an input mesh of mesh like the bunny or the hand. So, but you want to output it to a sphere or to a ball. So how did you choose the output mesh like a ball or some other shapes? Did you define it by the user or you just input a mesh?
We model shapes just by manipulating curvatures. So if you map the model to a sphere or to a cylinder, you can easily calculate its mean curvature and the Gaussian curvature. But for another easy way to design model is to editing do some filters on the Gaussian curvature and the mean curvature. If you want to make the input model to map to a general shape, you need to specify each vertex on it to a given target curvature. So this means you need to find the correspondence between two meshes. It's a hard problem. So in our paper, we haven't studied this problem.
Okay, I see. Okay, That's it. Thank you.
Okay, are there any other questions? If this is not the case, then we can go to the next speaker. So thanks once again, Mr. Funk, and please share your screen if possible now. The next speaker in this session is Mr. Park. He's doing a PhD at Seoul National University, and his research interests are focused on computational geometry algorithms. And the title of the paper he will present today is Surface-Surface Intersection Computation using a bounding volume hierarchy with oscillating toroidal patches in the leaf nodes. So, stage is yours.
Okay, thank you, Mr. Svayunas. I will start my presentation soon. Hi, my name is Youngjin Park, a PhD student at Seoul National University. In this talk, I'd like to present surface-surface intersection computation algorithm using a bounding volume hierarchy. This is joint work with 3 other authors. This is the outline of my talk. After motivation of this work, I briefly summarize the related previous results, and then I present the main technical parts of this work. Finally, I present our experimental results and conclude the paper. Why we are revisiting the SSI problem? First, recent developments of bounding volume hierarchy for freeform curves and surfaces make geometry algorithm efficient, because after constructing BVH in a preprocessing stage, we can reuse the structure without any time-wasting cost. Also, osculating toroidal patches give a high precision of surface approximation and simplify the geometric operations greatly. As the motivation of our work, let me show you the previous result of He et al. In this example, 2 cylinders are intersected. One cylinder is a rotated version of the other cylinder with angle theta. In the left 2 cases, the intersection curve has X junction. But in the right 2 cases, the X junctions are missing because the 2 cylinders are intersecting almost tangentially. On the other hand, our algorithm can detect the X junction correctly. These are other examples of almost tangential intersection. Please note that the rotation angle is much smaller than the previous examples. I'll explain some more details in the main part of my presentation. Surface-surface intersection problem has been studied for a long time. Therefore, lots of SSI methods are introduced in the survey articles, and many papers are mentioned and cited. Since then, there have been few publications in the SSI research. New results were shown for special types of surfaces, such as ring surface, swept surface, torus, and so on. Also, there are some numerical tracing technique for surface-surface intersection and detecting closed loops in the intersection curve by comparing the Gauss maps of the 2 surface patches. For geometric acceleration using osculating toroidal patch, there are some results in the past. We are also using toroidal patch for accelerate our algorithm. Let me explain about the bounding volume hierarchy construction process step by step. Basically, our algorithm can be applied to any type of tensor product surfaces on arbitrary degree, but for the convenience of presentation, we only consider bicubic Bezier surfaces as an original surface. From the bicubic Bezier surface, we can make a subpatch by uniform sampling. So, subpatch equals surface S on the specific domains. We can also obtain S hat by reparameterizing the subpatch. From subpatch, we have the 4 corner points by uniform sampling. With these corner points, we can make a bilinear surface that interpolates the 4 corner points of subpatch for all subpatches, and build a hierarchy structure of bilinear surfaces, which has a quadratic convergence. By projecting bilinear surfaces 4 corner points to the tangent plane at the middle point of surface, we can get planar quadrangle Q. Also, we can bound the maximum distance between S hat and Q, which is epsilon. And then, we can make a bounding volume by expanding planar quadrangle Q by epsilon. This is a graphical example of planar quadrangle swept sphere, QSS. Bounding volume with planar quadrangle is okay, but for more tight bounding, we replace planar quadrangle to rectangle R. With planar quadrangles plane and their bounding control points plane P, we can make a rectangle R. In some further step, we can obtain very tightly rectangle bounding volume and can make rectangle swept sphere RSS. To compare QSS and RSS, The size of the bounding volume of RSS is much smaller than the size of QSS. For more technical details, please see the paper. With BVH construction process, we can build a RSS BVH tree for two different surfaces, surface A and surface B. With 2 BVH, we can test the overlap between the RSS pairs and traverse the RSS BVH trees. If overlap exists, go down to their child node and test their overlap recursively, and collect all overlapped RSS leaf pairs. In our algorithm, each leaf node of RSS BVH contains their oscillating toroidal patch. The toroidal patch can be made by using surface curvature information at the middle point of the subpatch. Torus has a full range of curvature, so choose the specific domain of torus that not only the curvature at the middle point of toroidal patch and subpatch is the same, but also can cover both the subpatch's positions and the normal directions. Usually, the direction of the torus and the direction of the surface are not same, so we can represent the trimmed toroidal patch T hat. This can be done by projecting the four corner points of S hat to the toroidal patch and connecting the projected point to a quadrangle in the parameter space of the torus. Based on this parameter matching, we can bound the Hausdorff distance between S hat and T hat, and if the bound is larger than the given error bound, we can repeat the same procedure recursively by subdividing the Bezier surface into four pieces. One of the strong points of the toroidal patch is that it is easy to construct Gauss map and test their overlap because Gauss map of toroidal patch is bounded by four circular arcs on the Gaussian sphere. When the Gaussian maps have no overlap, the toroidal patches may have at most one branch in their SSI curve. In the case of having one branch, each endpoint of the SSI curve segment is located on the boundary of one toroidal patch. There are some more examples of a one-branch intersection. The SSI curve interior between two endpoints can be approximated by the numerical tracing method. By numerical tracing, we can get a union of intersecting toroidal patches and their intersection curve segment, but unfortunately, they may not even be connected. For example, two adjacent subpatches S hat are smoothly connected on the same Bezier surface, but two adjacent trimmed toroidal patches T hat are not connected, and they share no common boundary. To deal with this problem, we project all intersection points to UV parameter domain and construct G1 biax spline curves which approximate the sequence of intersection points. We project to ST parameter domain and measure the approximation error. That error is guaranteed to be within a given tolerance. Now let me show you our experimental results. We compared our bounding volume RSS with convex Hull and AABB of subpatches control points. First, this table shows the size of bounding volumes by BVH tree's height. The size of RSS tree is much smaller than convex Hull tree and slightly bigger than AABB tree. Toroidal patch is a tool that approximates subpatch and can apply all kinds of bounding volume, so we measured it separately. Let me show you our general intersection examples. From left to right in each test example, you can see two surfaces, red surface A and blue surface B are intersecting in XYZ. Red intersection curve at UV parameter domain on surface A and blue intersection curve at ST parameter domain on surface B. The leftmost one is the almost overlapping example, and the other two examples are missing X junction only slightly and forming two separate branches in an orthogonal direction to each other. This table shows the construction time for complete BVH trees. The construction time of our RSS tree is longer than AABB tree, but not more than convex Hull tree. This table shows the time taken in the BVH tree traversal. The convex Hull tree is again the worst in the traversal time, and our RSS tree is very slightly longer than AABB tree, In some cases, RSS3 is even faster than AAVB3 thanks to their smaller bounding volume size help to eliminate unnecessary computation. This table shows the pairs of overlapping lymph nodes in complete BBH traversal, so we can compare the tightness of bounding volume. The convexer tree generates the tightest bounding volume, so the number of overlapping lymph node pairs are the smallest, but its construction time and traversal time is the most expensive. The AABB tree generates the loosest bounding volume, so the number of overlapping lymph node pairs are the biggest, and even be influenced by the direction of the surface. On the other hand, our RSS tree generates overlapping lymph node pairs a little more than convexer trees. So, considering memory usage, construction, and tree traversal time, the RSS tree provides a good compromise for both space and time efficiency in the SSI computation for freeform surfaces. Now, let me show you some highly non-trivial test examples of freeform surfaces which intersect tangentially almost everywhere for showing the robustness of our algorithm. Two almost coaxial cylinders were intersected, with the angle between the two cylinders being very small degrees. We approximated cylinder by 4 bicubic polynomial Bézier surfaces within an error bound 10 to the minus 10. The first law is the whole image with almost coaxial blue and red cylinders, and tangential intersection curves are shown as yellow patches. The second law is a boundary curve of tangential intersection region, and the third law is zoomed view on their x-junctions. In these images, we rotate the red cylinder by 45 degrees about the axis of the cylinder and then intersecting with a blue cylinder. The cylinder seems to have not changed its shape, but the intersection curve is changed dramatically. We also repeat the same test to the saddle surface, and it works fine. As shown in preceding cylinder results, the yellow patches are ideally the surface of patches, which are within a certain one-sided Hausdorff distance, delta, to the other surface. So, for the exact computation, we should compute the intersection of a surface with the delta offset surfaces of the other surfaces. We left it as future work, and we take uniform samples from the osculating toroidal patch of one node to the other overlap osculating toroidal patch, and collect those within a tolerance delta, which is 10 to the minus 8 to the torus. Let me conclude my talk. We introduce a new algorithm for SSI problem for freeform surfaces based on bounding volume hierarchy, which has osculating toroidal patches in lymph nodes. By using a pre-built RSS BBH tree, we can speed up our algorithm and reduce memory usage than conventional SSI algorithms. Also, osculating toroidal patches have high approximation order. It is very effective for handling non-trivial cases of two freeform surfaces, which is tangentially intersecting almost everywhere. In future work, we plan to develop a new technique that can bound the tangential intersection areas more precisely and estimate the approximation error more accurately. Thank you.
Okay, thank you, Mr. Park. Are there any questions from the audience? I think you can easily unmute yourself or raise your hands or just ask in chat. Okay, then I can start. Can you comment on going beyond the case of bicubic Bézier surface? Like, how about cases of different degrees?
We also tested on different degrees of Bézier surface, and it works fine, but it takes some more computation time when the degree is up. Yes, when degree is down, the computation time is.
Okay, but how about the memory size for bounding volume hierarchy? Is it like also?
Yes. Actually, we compare the time and space complex the memory usage on our papers. Yes, and that's not quite big. Yes, and it works fine actually.
So there is also a related question on chat. What is the maximum degree of surfaces that you tried for?
We tried to degree 5. Yeah, degree 5.
Okay. Any questions? Any more questions? Okay, so then, yeah, you can ask more questions on Discord platform. And thanks for the presentation once again. And then I would like to introduce the next speaker in this session, who is Mr. Kim. He's a PhD student at School of Computing in Korea Advanced Institute of Science and Technology. His research interests are in 3D model processing, mainly compression, and today in his talk, Mr. Kim will present a paper on wavelet-based progressive fast recompression for large deformed mesh. So, please.
Yeah, thank you for introducing me. Yeah, I'm Young Kim. I'm in KAIST Geometry Computing Lab. Yeah, I will start my talk. Yeah, the title, yeah, I will start. Yeah. You might know the progressive compression of mesh. Yeah, it is the method for transmitting the data, transmitting the mesh data, easily over the network, to by serializing the mesh data into several different resolutions. These days, the data size gets bigger, so the data compression time gets much higher. Many related works consider the problem about reduction of file size or increasing compression speedup, or also reducing the visual difference between consecutive meshes. Yeah, they are mostly for the first compression, the original compression itself. But however, our main focus is about the second compression. For example, compress it again after deformation. Yeah. It usually costs as much as the first original compression time. So our main works is summarized like that. We use large 3D irregular triangular meshes, and we compressed it by using a progressive method. And after we deform the mesh with preserving its connectivity, yeah, especially preserving its connectivity. And then we want to compress it again faster than a previous one, which we called fast recompression. The main idea is reusing the compressed data, and we use wavelet-based method. Yeah, I will introduce the simple background knowledge to understand the wavelet-based method. Yeah, it is called wave mesh, introduced in 2004. The basic concept is that it reduces the mesh resolution by merging some vertices on mesh. The removed vertex is called wave child vertex, and its supporting two vertices are called parents. And yeah, the wavelet coefficient is generated from the function of the three components. It is very important coefficient to reconstruct the original mesh. And they apply the rate distortion optimization, which means that it reduces the visual difference between consecutive meshes by perturbing some geometry on mesh. Yeah, from now on, I will introduce our main algorithm. We first define the notation, the set R, which includes all of the vertices we want to deform. And yeah, in this figure, the only child vertices are removed to make a lower resolution meshes. And next, some of the vertices on the lower resolution mesh are affected by the original previous region of interest. So so that we want to so that our main goal is to find the vertices and also the wavelet coefficient affected by the original region of interest we want to deform. We add them. We add the non-child vertices into the set R, and the child vertices are add into the W hat. These notations are different, are a little bit different with our papers. To achieve our goal, we made the four-step rules, which we called a propagation algorithm. I will introduce the detail in the next slide. The first step is vertex propagation. In this step, for every non-child vertices, they still remains at the lower resolution mesh. So we add them into our set R. And next step is wavelet propagation. In this step, I mentioned that the wavelet coefficient is generated from the function of the three components, parent and its child. So parent vertices are parent vertices directly affects to the wavelet coefficient. So so we add all of the children of parents in the region to the set W hat. In this example, the parent is the vertex A, and their children are added to the set. And in the same region, the child vertex itself is also added to the W hat. The third step is also on a propagation. It is more complex than others. However, it is closely related to the race distortion optimization, which means that I already mentioned. We first set the radius constant k, and we add all of the vertices in the circular region with radius k at centered at the parent of each children we already found. In this example, we already found the blue X marked vertices as children, and their parents marked as red. In this example, we set the k equal 0, so the only parents are added to our set R. And the last step is modification. In this step, we recalculate all added elements by using the analysis filter. The filters directly extracted from the previous compressed data without recalculation. It is very important. So we can reduce the recompression time very much. From now on, I will introduce our experimental result. We use a large mesh dataset with up to 5 million vertices. It includes the a singly connected irregular triangular meshes only. The first result is full deformation. In this experiment, we deform entire vertices of mesh, and for example, you might think applying translation to the mesh, and then we compare the recompression time, which we call RCT in this table, and to the original compression time, which we call the CT. The table shows that the recompression time is up to 17 times faster than the original compression time. The next one is local deformation. In practical situation, we may want to deform a very smaller region relative to the original size. So we randomly chose the 5% of local circular region of interest, and then compare the recompression time. The table shows that recompression is up to 33 times faster than the original compression time, which is very faster. And the last experiment is that we changed the size of the modified vertices, modified region, the region of interest. We noticed that the recompression time is proportional to the size of modified vertices, and the recompression time is suddenly decreased when the size is very, very small. So so it gives higher performance, much higher performance when we have a very large mesh, and at the same time we have a very smaller region relative to the size. In summary, we made a structure and we made an algorithm for fast recompression using previously compressed data. And our result shows that the recompression time is up to 33 times faster in practice. And also we can handle large mesh data. And also we can consider the following issues about our work. What about view dependent rendering? It is for decreasing the reconstruction time, deformation time before it is recompressed. And what about direct file modification, not indirect high-level element-wise modification? And what about connectivity non-preserving deformation? These will be considered in our future work to improve the practicality of our work. This is a reference of our dataset. You can find the dataset in the site. And thank you. Thank you for listening. This is the last slide. If you have any questions, feel free to ask me. Thank you.
Thanks a lot for the presentation. So we have plenty of time for the questions. Does anyone has question? So you can ask loudly or in chat. Okay, then I have a question. What is the main limiting factor of your approach? Like, is it computer memory or computing time? Because in the paper you mentioned that you can go until the mesh with 5 million vertices. Can you go further actually?
It has, there's no limit, no theoretical limit of our work, but it has some issues about practical situation. We have, the compression, during the compression, there are many components we have to store in the memory. So we Yeah, so we use 48 giga RAM for the largest mesh we have. Yeah, it has the 5 million vertices. So if we want more, if we want the mesh with more vertices, then we have more computing power. Yeah.
Okay, thanks. And there is one question in chat. So is there any loss of data when the mesh is compressed?
There is no loss because we use the compression method. It is called wave mesh then, and it is the lossless compression. It supports. Yeah.
Okay. Okay, are there any questions? Any more questions? Okay, then you will get, I'm sure you will get more questions on Discord platform. Thank you, Mr. Kim, once again, and thanks to all the speakers and session attendants. So SPM has another session on geometry processing on Wednesday. Next in the program, we have a fabrication session of SMI and SOPA workshop. So also don't miss the opportunity to visit Discord platform and interact with speakers and paper authors. Okay, so enjoy the conference.